my name is Malika Sai. I'm a second year animal science major, and this is problem 17 from chapter 5.2 of the thermochemistry section. So the question is, one beaker contains 20 ml of 1.6 moles of hydrochloric acid, and a second beaker contains 60 ml of 0.4 moles of sodium hydroxide. Both solutions were initially at 20 degrees Celsius. We pour both beakers into a large insulated container which contains 10 grams of ice, initially at negative 60 degrees Celsius. Calculate the final temperature of the resulting solution. Note that the heat of neutralization is negative 57 kilojoules per mole. I like to start out with writing down my variables first. So first we know we have 20 mils of 1.6 moles of hydrochloric acid. We also know that we have 60 mils of 0.4 moles of sodium hydroxide. And we know that both of these solutions are at 20 degrees Celsius. Then we have 10 grams of ice, and that initial temperature is at negative 60 degrees Celsius, and then our enthalpy of solution is negative 57 kilojoules per mole. Now let's write out the steps that we're going to take in order to solve this problem. So the first step that we should take is to find the limiting reactant of the neutralization reaction between hydrochloric acid and sodium hydroxide. The second is that we should find the Q of the system, the third, Q of the surroundings, and fourth, we're going to finally solve for temperature. To find the limiting reactant, we first know that we have 20 mils of 1.6 molar of hydrochloric acid. We also have 60 milliliters of 0.4 molar sodium hydroxide. So the hydrochloric acid is going to react with the sodium hydroxide, giving us water and salt. And for this reaction, we want to focus on the moles of water formed for our limiting reactant. Now we should make sure that our equation is balanced. So we have 2 hydrogens, O, and O, chlorine, and 1 sodium. So our reaction is balanced. So first, let's find the amount of moles of water produced by the 20 mils of hydrochloric acid. So we start with 20 mils, and we know there's 1,000 milliliters and 1 liter. And we know in this 1 liter, there's 1.6 moles of hydrochloric acid. And using the stoichiometric ratio, we know for every 1 mole of hydrochloric acid, there's also 1 mole of water. So when we multiply all these numbers together, we get a grand total of 0.032 moles of water. So now we're going to do the same for the sodium hydroxide. So we start with 60 milliliters, and we know that in every 1 liter, there's 1,000 milliliters. And for every 1 liter of the solution, there's going to be 0.4 moles of sodium hydroxide. Now, using the stoichiometric ratio, we know that for every 1 mole of sodium hydroxide there's also 1 mole of water. So when we multiply all these numbers together, you get a total of 0.024 moles of water. Since this is less than 0.032, this is our limiting reactant. Now let's find the Q of the system. So our system is the hydrochloric acid plus the sodium hydroxide, giving us water and salt. HO plus NaCl. So for this equation, we're going to be mainly focusing on the water, since it has properties that we know it can easily measure. So the equation that we're going to use to find these is Q equals mc delta T of water plus N delta H, which is the enthalpy of neutralization. So since it's an acid-base reaction, it gives off heat, so that's what this N delta H is that we take account for in our equation. So now let's rewrite down our variables so that we don't get confused. So M is our mass of water, right? But we were only given mass of hydrochloric acid and sodium hydroxide. Well, since both of those together gave us water, we're going to add those two masses. So we're going to add 60 plus 20, that gives us 80 milliliters of water. And water has a density of 1 gram per milliliter, so then that gives us 80 grams of water. Our specific heat of water is 4.184 joules per gram degrees Celsius. Our change in temperature of water is going to be TF, which we're solving for, minus our initial temperature, which is 20 degrees Celsius. Our moles of water we found out from the last equation, 0.024 moles. And then our enthalpy of neutralization is given to negative 57 kilojoules per mole. So now we can just plug this all into our equation. So our mass of water, 80 grams, times the specific heat, which is 4.184 joules per gram degrees Celsius, times the change temperature, TF minus 20 degrees Celsius. Add that to our enthalpy of neutralization. So our moles of water, 0.024 moles, times the enthalpy, negative 57 kilojoules per mole. So when we further simplify this, we're going to get 334.72 joules per Celsius times the final temperature minus 8.05 kilojoules. This is equal to the Q of our system. Now we're going to find the Q of the surroundings. So our surroundings, it starts as ice, and eventually it goes to water. And ice to water, that's undergoing a phase change. So our equation is going to be a little different than just Q equals mc delta T. So first we're going to look at our phase change diagram. So you can see where all the T is for temperature, and capital T is for temperature. Where all the temperatures are increasing, that indicates it's in one phase and the temperature is increasing. So here it would be ice, and here would be water, and here would be gas. So this is where ice is heating up, water is heating up, and gas is heating up. So you can see where it kind of plateaus, all these places where temperature stays constant, all these places. That's when the substance is undergoing a phase change. So from here, it's going from ice to water, and then water to gas. And then where all the places where temperature is increasing, the equation is going to be Q equals mc delta T. And for all the places where it's going a phase change, the equation is going to be N delta H is equal to Q, where H is the enthalpy of fusion. So in our equation, we're going from ice to water. So we start at ice, and then at the phase change, and end at water. So then our overall equation is going to be the mc delta T of ice. So mc delta T, and this is of ice, and then it's going to undergo the phase change. So N delta H, this is from ice to water. And then it's going to then the water is going to heat up. So plus mc delta T, and this is of water. And all of this is going to be equal to Q. So we have all of our variables written down, right? So let's start plugging them in. So our mass of ice is 10 grams. And then the specific heat of ice is 2.09 joules per gram degree Celsius. And then our change in temperature of ice, well, ice can only be at 0 degrees, right? So it's going to be 0 degrees as our final, minus negative 60 degrees, which is our initial. And then we're going to add that to the phase change. So then we're going to need the moles of ice that we have. So we have 10 grams of ice divided by the molar mass of 18.016, and that'll give us our moles. And then times that by the enthalpy of fusion, which is 6.01 kilojoules per mole. And then we're going to add that to the mc delta T of water. So the mass of water is 10 grams, because that still hasn't changed. We're not going to gain or lose ice or water. And then the specific heat of water is 4.184 joules per gram degree Celsius. And then our change in temperature of water is going to be our final temperature minus our initial, which is 0. So now we just start to solve. So for our mc delta T of ice, we're going to get 1,254 joules, or 1.254 kilojoules. It's the same thing, you just divide by 1,000. Then add that to our phase change, which is 3.31 kilojoules. Then add that to our mc delta T of water, which is, we're going to get 41.84 joules per Celsius times the final temperature, which is our unknown. Then when you further simplify this, you're going to get 4.56 kilojoules plus 41.84 joules per Celsius times final temperature. This is equal to our Q of our surroundings. Lastly, we're going to solve for final temperature, and we can use this expression Q system equals negative Q surroundings in order to find this temperature. A Q system is the hydrochloric acid reacting with the sodium hydroxide, giving us water and salt. Remember, we're going to focus on the water. For our Q surroundings, that's going to be our phase change from ice to water. So we're going to use the two equations that we got in our last two sets of problems in order to solve. So our hydrochloric acid equation for our Q system, we got that to be 4.56 kilojoules plus 41.84 joules per degree Celsius times final temperature. That's going to equal to be negative of our Q surroundings. That's going to be negative 334.72 joules per degree Celsius times final temperature minus 8.05 kilojoules per mole. My bad. Kilojoules per mole. Units are important. So now we're going to just distribute this negative to the right side of the equation. that is going to get negative 334.72 joules per Celsius times final temperature plus 8.05 kilojoules per mole. That's going to be equal to the same thing. So 4.56 kilojoules plus 41.84 joules per Celsius times the final temperature. So now we're going to combine like terms. So I'm going to add 334.72 on both sides. And I'm also going to subtract 4.56 kilojoules. So when we do all that, these cancel out. And then we are going to get 376.56 joules per Celsius times final temperature is equal to 3.49 kilojoules. So now if you look at our units, we have joules and kilojoules, and we can't combine those like terms because they're not like terms. So we're going to have to convert joules to kilojoules. So 376.56 joules, and then in every 1,000 joules, there's 1 kilojoule. And then that's going to give us 0.376 kilojoules. So then, now we can combine like terms. So 0.376 kilojoules per Celsius times final temperature is equal to 3.49 kilojoules. So divide both sides by 0.376 by 0.376. And then when we do that calculation, our final temperature is equal to 9.26 degrees Celsius, and that's your final answer. Congratulations, you made it through the whole entire video. Thanks for watching, and I hope this helped a bit.